Greetings and welcome, friends. We're continuing our look at shapes of distributions. That's right, friends. And example 3 here, it's asking us to compare these data distributions. Oh, and it's got some data regarding text messaging and the use of emoticons. What? Man, feel free to comment below this video the emoji that you're feeling about this problem right now. Except there's no emojis in YouTube, right? So it says emoticons are graphic symbols that represent facial expressions. Sometimes they are used to convey a person's mood in a text message. The double histogram, why do you think this is called a double histogram? That's very intuitive. Yes, because there's 2 of them. Shows the distributions of emoticon messages sent by a group of female and a group of male students during 1 week. Compare the distributions using their shapes and appropriate measures of center and variation. What do you mean? What's incorrect? What's incorrect about it? What's not true? Okay, so a student's saying that this isn't correct, that it might be true for that data, but in general, it might not. Okay, and that's an interesting thing in terms of statistics, is that we can analyze a subset of the entire population, and the more or the larger that group that I survey is, if I survey 10 people compared to 100, compared to 1,000, compared to 1,000,000 people, the more people I survey, the more data I get, the more accurate that data is at making predictions about the entire group. Now, it would be true for me to make conclusions on average the differences between these male and female students, but yes, it would be incorrect for me to say all male students or all female students blank, 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 right? Whatever conclusion I would make. That would be an inaccurate statement and would be outside of the bounds of statistics. Okay, but statistically, we can analyze differences among all sorts of different outcomes. And you're right, we have to be careful what generalizations we make versus, right, the specifics that we do observe here. So let's see. So let's take a look at this. So the shape of this distribution, what type of shape would you call this? It's kind of symmetric, right? Not exactly. Kind of symmetric. What shape do you call this? This one is skewed. Which way is it skewed? It's actually skewed right. Which, because the tail tapers to the right. But what's weird about the skewed data terminology is that that means if something's skewed right, that means most of the data is on the left. Okay, let's talk about what's the best measure of center. For this one, what would the best measure of center be? Mean. And what would the best measure of center here be? All right, median would probably be somewhere about there. All right, median being the middle number, mean being the add them all up, divide by how many there are, average. They're both types of averages. And then as far as distribution, how would I describe the variation? What's the best measure of variation? For symmetric graphs, we would use standard deviation. Yep, we'll do more with that today and tomorrow. Standard deviation. And for this one, I would do the 5-number summary. All right, so I would imagine some sort of box and whisker. This graph might even just have no right whisker. This one might end up looking something like this. Or maybe no left whisker. Yeah, my bad. Thanks for helping me out, friends. Because, yeah, so much data might have landed here that more than 25% lined up with where the edge ended up being, based on what I currently know. I only have a distribution. I don't know all of those data values. You know, most of those could have been 8 Most of those could have been 0. I'm not sure. I just know that 14 landed in the 0 to 9 category. So that's what we end up having. What comparisons would you make? What analysis would you say? On average, what would you say about these two groups? So on average, right, females use more emojis. Right? And then the more data that I have, the more accurate that statement becomes. Actually, not in this course, but if you ever take statistics in high school or college, you'll actually eventually be able to say with what % certainty you could conclude that this % of the population will use this number of emojis or something like that. All right, so there's one statement we could use. What's another statement we could make? How about in terms of the distributions, the variation here? Look, if I did take range, the range here goes from 0 to 59. The range here is just going from 0 to 39. So the range here is 59. Here the range is 39. So what would you tell us? Okay, that's an analysis, once again, of the red component, the measure of center. But if I'm describing the variation, I could say that have a greater variation of emoji use on average. Right? Yeah. So there's a much broader type of outcome when looking at the data regarding females, whereas the males using emojis was a much more densely clustered group of outcomes. So for instance, would I expect males to use 50 to 59 emojis? It could happen. And for this data, it was 0. But if I was making a prediction, like if I survey now 1,000 people, would I expect to find a guy who's using 50 to 59? It could happen, but it would be unlikely, right? A small percentage would be what I would expect. Because, yeah, this tail tapers off rather quick. All right, so that's some of the ways that you could compare different things, okay? All right, I'll leave that up for un momento. Yeah. Did you find what you need? Find what you look for? Text yet? It's okay. I need an outro song? Really? Yeah. I don't have settings to make the screen not dim when I... Okay. I'll move on, but if you need to look at that during any class quest or later on today, feel free to bring it back. So another interesting thing we did it during the kind of the exploration today. We talked about what % landed in a particular batch. Okay, what % landed in a range. Now, we've noticed that many real-life data sets have distributions that are called bell-shaped. This is the bell-shaped curve. No? Okay, that's fine. But that's what they call it. I mean, we don't have a lot of bells these days, but think like Liberty Bell sort of shape. And approximately they are symmetric about the mean. In a future course, not this one, you will study this type of distribution in detail. But one of the interesting things when analyzing it is that, so the mean we called x bar, right? We've already used that terminology, that symbol before. And we've also used little sigma for standard deviation. That if I look one standard deviation above and below the mean, I tend to get about 68% of the data. So this is a way that standard deviation ends up being a really helpful number for me. That if I calculate standard deviation, right, using that long table, that long formula we did, or maybe a spreadsheet, I can now then make predictions about what percent of the data would land in a particular batch, okay? So within 2 standard deviations, we'd actually expect to see about 95% of the data lands like that. Now, not all data ends up being a bell-shaped curve, but a lot of times things like, right, the chest size of Scottish militiamen in the mid-1800s, there's going to be a standard deviation, a bell shape to that, and we would expect a certain percent to land within a certain region, okay? And so we'll actually be able to analyze this quite a bit. Yeah, here's an interesting thought. Yeah, if 68% land there, what percent would land just between here? Yeah, what percent would land just there? No? Well, if both sides are 68, yeah, then this is going to be 34%. And actually, I'll end up giving you a chart tomorrow describing kind of these individual zones and their percentages. And so, yeah, so we can actually make kind of different predictions based on these. We can understand with just having the mean and a standard deviation, we can make understand a lot of things about a large set of data or a large population and different things like that. So whether you're studying like biology and animal populations and sizes of animals that are being observed, whether you're talking about the coal being used per year, and maybe that varies a little bit, but in general maybe it's about the same. Right, there's all sorts of different things that you could analyze and make predictions. Oftentimes you've seen this used. Last year was a voting year for the United States, and as the votes come in, you actually would see them make predictions based off of the data that was coming in, even before all of the votes were in. They would actually say we're like 95% sure based on this result that, right, these are the, 51% vote this way, right, 48% vote the other way, or whatever it happened to be. And there'd be like a margin of error that the more votes that would come in, the more certain they would be of the outcome. It would be less likely for things to suddenly flip-flop. All right, so that's one of the things that statistics allow us to do. Let's take a look at example 4. How many pairs of shoes they own? Okay, so here is a table that surveyed men and women of how many pairs of shoes they own. Okay, actually, oddly, they didn't survey the same number of people. That's unfortunate. Usually you want to survey the same size of each group, and you want what's called a random sample. Okay, a random sample. Because I mean, if I survey people in Brattleboro regarding what their favorite football team is, I'm assuming a decent chunk of them would like the Patriots. A decent chunk would probably like some New York team or something like that. But I couldn't then be like, see, look at 58% of America likes the Patriots based off of a survey done in Brattleboro. That would be inaccurate. To get a statistic about the entire United States, I would need to have a random sample where I kind of picked people from all over the U.S. and not just people that happen to be walking out of Gillette Stadium after a particular game. That would completely mess up my data. I shouldn't be able to make predictions based off of that, right? So here we go. Make a double box and whisker plot that represents the data. All right, so box and whisker plot. Here we go. You don't? Oh, I'm sorry. So I'm going to draw a number line. What's my lowest value I gotta go at least as low as 2. And what's the highest value? Oh, there it is. Nope. 40 was the number of women that were surveyed. Notice they actually labeled a bunch of these values for us. So 24 is as high as I need to go. So let's see. Let's count by twos again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and... Okay, so I'm going to make a box and whisker plot. I'll do green and red. So let's see. For green... Nope, that's white. Go. Better. The minimum score was 2. It'll be all right. All right. Is there room on the next page or in any margin? I'm sorry. Wow. I usually do a better job of giving you space. What about right next to that bell curve? Yeah. The maximum was 17. The first quartile was at 5. The median was at 7. And third quartile was at 10. So, box and whisker plot for this. Number of shoes owned for males was that. Let's see, for females, the minimum was 5. Okay, so for them, I'm going to put them kind of top of each other so that way I can compare them more easily with just a single number line. So 5, the maximum was 24, like so. First quartile was at 12. 14 was the median. And quartile 3 was 17. Great idea. So here's my double box and whisker plot. It says describe the shape of each distribution. Based on this outcome, this looks pretty symmetric. How would you describe the shape of the male distribution here? It looks like the data is more densely compact over on the left side, right? Because each of these regions represents 25%. So if the data is dense on the left side, that means that graphically speaking, that would be skewed right. Right? That this is longer than that. Okay? Let's see. As far as describe the shape. Yeah, I already did. Compare the number of pairs of shoes owned by men to the number of pairs of shoes owned by women. Now, this would not be something that I could make a generalization about all men or women. There's going to be outliers in each of those groups. You might find a guy who owns 50 pairs of shoes, and that can happen. This is just saying they surveyed this number, and now I can make generalizations, right? On average, you might be able to make some. So, all right, if I want to compare those, which has the greater number of shoes owned? Right? If I'm using the mean for women is 8, I would use mean when I have a symmetric graph. And since the male is skewed, we would use the median. Nope. Sorry, I lied. The mean for women was 14. The median for men was 7. So you could say, on average, men own half as many shoes as women, right? Something like that. That's on average. Okay? So that's something that I could say. What about in terms of their distribution or how varied they are? if I look at the range here, 24 minus 3, was 3 the minimum? 5, man. Range is 19. Here, range was 17 minus 2, 15. So you could say that the number of shoes owned by women vary more than men. Okay, that's another thing I could say. I could also look at this in terms of direct lining up here. Notice this. I could say 25% of women own more shoes than 100% of the men here. Right? They both happen to line up there. That's an interesting thing you could say. I could even analyze that a little bit differently. I could say, I mean, there's lots of things you can say. So if this is 25, this is 25, this is 25, this is 25, I could say these 3 25s, so that's 75%, own more than 75% here. Right, based on that. They actually probably own more than 75%, because this region is only 25%. So there's all sorts of different types of analysis that we could do. And then how about this? About how many of the women surveyed would you expect, so this is a prediction, it's not exact, to own between 10 and 18 pairs of shoes? So between 10 and 18. Why does it have to be more than 50? Yeah, 50% is right here, right, between those. So this is more than 50. So yeah, anywhere between, right, if you said 60%, maybe you could have even said up to like 70%. It's just a guess, right? But you'd be able to make a prediction based off of that outcome. Yeah? Are you feeling it, Mr. Krabs? All right. Well, I think that's good for today. Thanks for watching. Mis amigos.